You can see in terms of what it's dealing with, the idea of finding the length of a curve. So what I have in words is basically, let's say we wanted to find the length of this curve. So I'm going to draw this on a little XY plane. What we could do to get that started is put a dot right here and then put a dot right here. Draw in a line segment connecting those two dots. And then the whole, like, this is our second point, this is our first point. And then do you remember the good old-fashioned distance formula? Couldn't we now go ahead and use the distance formula to find the length of that red line segment? So while that'll give us the length of that red line segment, it obviously isn't the length of the curve. If that was like a string that we could straighten out, the curve would be longer than that red segment. But at least it gives us an idea of how long that is. It's an approximation. So like a lot of things we've been doing, we start out with the idea of an approximation. How could we get it to turn into an exact value? Well, if that's an approximation, what we could then do to make it a little more accurate, instead of that one, let's just say I use some more points. So let me put some points right here. And let's say I draw a line segment connecting those two, those two, those two, and then those two. So now I have 1, 2, 3, 4 line segments. If I now added, so this is where our little sigma comes in, if I now added those 4 line segments, just again using the distance formula here, I hope we would all agree that that is still an approximation, but it would be more accurate than the one single line segment. So now you're kind of seeing some common themes of things we've talked about before. If 4 is more accurate than 1, then we would probably want to add even more. And the more line segments we add, the more and more it's going to really resemble this curve, and the more accurately it's going to find the length of that curve. All right, agree with all that, hopefully. What that then gets into is like we did with the area and rectangles. Instead of a Riemann sum where we're just dealing with 4 or 10, what we would ultimately want to do is to take this sigma sign, where n is the number of rectangles before, now it's the number of line segments, and figure out, well, what limiting value would we approach as the number of line segments we use become more and more and more? Because whatever that is, that's got to be the length of that curve. So that's kind of what the top says, is kind of what the middle of the page says when you look right here. This is our distance formula. Just remember, just know like delta x is the same as just x2 minus x1. And then delta y is the change in x. So it's just different ways of, or change in y. It's just a different way of expressing it. So that's what we talked about at the top. What we would want to do though is get these in terms of the same variable. Again, Calc 1, even Calc 2, we don't deal with multiple variables. So all this stuff is single variable. So we don't want multiple variables there. So one of the things that we can do or use that takes into account a curvature and how these are defined is the good old mean value theorem. So we haven't talked about that in a while, although it was on that cumulative assignment. And the mean value theorem states that the average rate of change would have to equal to the instantaneous rate of change as long as we're dealing with a continuous function. So what we're going to do with that is we're going to solve that for the change in y. So if I ask you to solve that real quick for delta y, why don't we just multiply both sides by the delta x? And what we would end up with is that f prime of x, or f prime of c, multiplied by our delta x. Although it went off the screen here. What we're simply now going to do is a substitution. So instead of delta y, this is what you're going to see next when I lower my screen, we're going to replace delta y right here. We're going to do a substitution with that. So if we now scroll down, that's sort of what you see right here. Or no, that is what you see right here, but we need to do one extra step or two. So come off to this side. This is now, instead of delta x squared plus delta y squared, we've done that substitution. And then what I want you to do to clean this up is, since both of these are getting squared, we're going to square each of them individually. So we're going to write this as f primed of c squared times the delta x squared. What you would then notice, hopefully, is we have a common factor of the delta x squared, and then I cross it out. So since they both have a delta x squared, we're going to factor that out. So if I take out a delta x from this term, it's going to be a 1. If I take out the delta x from this second term, all I am left with is my derivative squared. And then the delta x squared I'm going to leave on the back end. So instead of factoring and putting it out in front, I'm going to factor it and put it behind. What that now creates is this single term now underneath a square root. So I have a square being taken the square root of. So what that allows us to do, we would only now underneath the square root have f primed of c squared. And then the square root cancels out that square, and all we are going to have left over is a regular old delta x. And you can kind of see where this is going now, starting to kind of look like our definite integral. This is still our approximation. What we have talked about now, if I go ahead and do the limit as n goes to infinity, so the more and more line segments that I put in there, and we're just dealing with the distance formula, the whole limit of a Riemann sum is one of the handful of things that just walking out of here at some point at the end of the year that we can recall. That's what a definite integral calculates for us. The limit of the Riemann sum is taken care of by the definite integral. So when we take that limit, creates our definite integral, we have this square root, and then it is simply 1 plus our derivative squared, and then in terms of dx or dy. So long story short, we kind of went through all that. So you understand there's a reason this comes about like it does. We're not just making it up. But long story short, you need to get this memorized. I will not ask you to kind of go through all of those steps. What I have highlighted right here in blue, just get that memorized. A question or two that you're going to see on the test, very straightforward. It should be a gift. These should be 2 to 4 points that you're getting correct no matter what. So you'll see, these are pretty straightforward. There are little tweaks we'll deal with later in the year, but for the immediate future, here's what you would need to be able to do. So if you go to number 1, we want you to find the lengths of the following curves. All we're doing is this formula right there. So if we know our formula is the integral from a to b, and then 1 plus the derivative squared. And since we're written in terms of x, we're going to do this with respect to x. The limits can't get any easier with this problem. I tell you what they are. So they're going to be 0 to 4. As long as we know the derivative formula, we just plug that in. So let's take our equation here. Our derivative should be 3 halves, and then subtract 1 from that power to the 1/2. So then we replace the derivative with 3 halves and then root x. I will then ask you to do one of two things on the test with these. You'll either do a math 9 and just throw this into your calculator. We should be pretty good at that at this point. Or just simplify this. This is the most common. 3 halves squared is going to be 9/4. The square root of x squared is x, and I would just have you find the integral. You would never be expected to do this by hand. All right? And that's pretty much it. If you go to number 2, now it's a familiar curve, so let's make clear what we're finding when we do this. I'm going to sketch in y equals x cubed. So here's y equals x cubed. And let's say this is 0, and let's say this is 3. So when we calculate this right now, what we're really finding is the length of our curve in this interval right here. If it was a string, and we laid out the string to model that cubed graph, and then only went from 0 to 3, and straightened it, this would be the length of that string in that little interval there. So the length should be, our limit's pretty straightforward, 0 to 3. And then we just need to know it's always the square root of 1 plus the derivative squared. In this case, it's written in terms of x. So the delta x is our dx. And then the derivative of this, I don't even need to really show it, is just 3x squared. Simplified, 1 plus 9x to the 4th, and then dx. However, like a lot of the things we've done in the chapter, what happens if our equations are written in terms of y? So that's what this next section now deals with. What if it's x written as a function of y? I rearranged it. You really don't need to rearrange these. I just did it to differentiate between in terms of x versus in terms of y. But you can still just do it normally as 1 plus the derivative squared. But now that our equation is written in terms of y, we're going to do this with respect to y. So if I look at this equation, now that we're going to do it in terms of y, all we really need is the derivative of this, which would just be a cosine of y. That's what we plug in here. Limits are easy. I tell you what they are, 0 to pi over 2. Hard to screw that up. And then that's the setup. And last one, number 4. Go ahead and set that one up. It's really the gist of it. It's the last problem in the notes. It really is this easy.
Is 1 plus cosine squared of y equal to 2 minus sine squared of y?
Oh, God. Say that one more time now.
It might have the same, but I was wondering, 1 plus cosine squared of y is the 2 minus sine squared of y.
2 minus sine squared of y?
Yeah.
That's not ringing a bell. 2 minus sine squared of y. 1 plus cosine squared of y.
I need to waste your time.
Yeah, I suppose it is. Right? Because you're going to get a 1 plus cosine squared y. Yeah, I suppose you could do that. It doesn't get us anywhere, but it's certainly true. Next chapter, we're going to have to revisit all those identities that you learned last year. So let's just keep it till next chapter. All right, so now this setup, you're going to have your square root, 1 plus your derivative squared, since this is a equation written in terms of y. Our derivative, this would just be 4y plus a 1. The only thing you do need to just be careful of is making sure that if we have an integral with respect to y, that your limits need to be y's. So just be careful of that. So when we look at these points, we want to make sure we use the y coordinate of the first point and the y coordinate of the second point. So our limit should just be 1 to 2.
Mr. Vanier,
Yes, sir.
in terms of the derivative, I think you missed a exponent in the full y, which we call y.
Say that one more time now.
Never mind.
Yeah.
What?
You made a mistake and I corrected it.
I made a mistake?
No, you made a mistake and I realized.
Oh, so I'm good. All right. All right, any issues with that? We go with that. So the question or two you're going to see on this test regarding these will not be any more difficult than this. So you want to make sure you're going to get those right. The next thing then is if you go to the first little review that I have, it looks like this in that packet. So normally how this test plays out this first day, when you're doing all the discs, the washers, the area, cross sections, all of that, there's 4 or 5 questions without a calculator. You turn that in, I give you the second part, which is with a calculator. The AP test used to be 3 non-calculator AP questions or free response, and then there would be 3 calculator free response. These sorts of questions, the discs, washers, cylinders, those were always on the calculator part. About 6 years ago, they went to 2 questions with your calculator, 4 questions without a calculator, and ever since, these have always been non-calculator questions. In our current situation, it's hard for me to say, okay, take this part of the test without a calculator, and then when you're done with that, go ahead and pull out your calculator and do the second part. So I'm not naive in terms of what's going on at home. There's no way to monitor who has a calculator, who doesn't. So I'm not going to do that Tuesday because there's really no way to monitor it. I still want to go over this. This is why I made this review once that started to happen on the AP test. To make sure we understand how could we handle this if we don't have a calculator in our hand? What sort of functions do the AP test writers expect you to be able to know without being able to throw it into your calculator? So we're going to go through this. We're going to not use our calculator. And then just kind of keep in mind long term, come May 4th or 5th, whatever that our test date is, when you take that, kind of recall, we'll obviously have some time in between to refresh our memory on this. How can we handle these without a calculator where you don't throw math 9 in all the time? So for number 1, here are a couple of equations. Go ahead and make sure you can graph this without your calculator. They don't give you anything crazy to graph. They're not giving you like cosine of x times e to the 3x and expecting you to know what that looks like without a graphing tool. But these two equations, we should definitely be able to graph. As you're doing it, keep in mind that you're in the first quadrant. So hopefully when you sketch this in, we don't necessarily need the x squared graph over here. We don't need the horizontal line 4 over here, but certainly over here in the first quadrant, we should have that as our squared graph, and then the horizontal line 4. So as a rough little sketch, this should be the area that we are dealing with. No rotations yet. So this is how this chapter started. We just had a simple area, and we're going to be adding up the rectangles within that area. So then we talked about how we had all these rectangles in here, and when we add them all up, that would give us the overall area of that space. So since they're rectangles right now, the way we set this up is our area is the sum of a bunch of rectangles who have a height and a base. The way this was written, y equals x squared, that implied we wanted to do our rectangles vertically, so that's why I drew in those red rectangles vertically. Therefore, the base of all of them, like how wide they are, they would all be measured as the change along the x-axis, so our base would have been dx. And then the height, when we did these, is when we first started the idea of top minus bottom or right minus left. Since our rectangles are verticals, we're going to be doing a top minus a bottom. The top is 4. The bottom is x squared. Since we're using the variables x everywhere, our limits are in terms of x, so our first rectangle would have started at 0, and then we would have continued to draw them until we got to right here at this point. So we would just want to know, what is that intersection point? You probably don't even need to set up an equation to figure that out. It's where 4 and x squared hit each other. So normally we set those up, but that you probably just know is going to be 2. So then that is our upper limit. We've gotten used to doing math 9, because we've been doing that a ton here the last couple of weeks. So what we now need to recall, if we don't have the calculator in our hand, the integral also tells us that we would do the antiderivative of our function if we're doing this by hand. So the antiderivative of 4 would have been 4x, and then x squared would give us x cubed divided by that new power, and then we evaluate it over the interval of 0 to 2. Upper limit gets plugged in first, so we throw in our 2, we get 8 minus 8/3. It is not uncommon, they typically do give you a limit of 0, either as your upper or your lower, to make it somewhat more manageable. So the nice thing about that is when the lower limit of 0 gets plugged in, you're just going to get a minus 0. If it is a free response question, this is all you need to do. In fact, I would strongly recommend just leaving this so you don't screw up this fraction if you don't have a calculator in your hand. If it's multiple choice, because there is half multiple choice without a calculator, then you obviously need to be able to do that. So 8 minus 8/3 is 24/3 minus 8/3. Our final answer should end up being 16/3. Yeah, Ethan?
Like, I know that you just ended there, that's just, but I'm like always scared that, like, what if I ended at this spot? Is it how it's all?
So the free response portion, once we were to be here, you can stop.
But like, that's just for this question, like for others, for like a question in general, I don't really know like when to stop. Is it like when you can
When all of the calculus elements of it are done. The simple adding and subtracting numbers is
for sure like that.
100% sure. Yes, no doubt.
Making nervous.
You'll see another one here we'll talk about where you can just leave it. So that's the type of equations I'd expect you to know without a calculator, and that's the steps we would want to take. All right, number 2, you're going to use that same exact area. So go ahead and sketch that in again. Number 1 is the first thing we did in the chapter, just finding a simple little area. The next thing we did in this chapter is we took that area and we can now start creating different sorts of shapes by using that as a base and putting different things on top of it. That's what this one is. So the area enclosed by the graph in number 1 is now the base of a solid. The cross sections of the solid, this is important, perpendicular to your x-axis, so that means you got to put them in vertically, are going to be semicircles. So what we did is we sketched in a semicircle. If I could now take that semicircle, I want the diameter of that semicircle to lie on my paper, on my screen, all right, on this yellow space. So I'm going to take this side right here, and I'm going to place it in that region. The circular part is out in front. In 3D, it would be towards us. In 2D, I'm going to draw it kind of going off to the right. I have another one over here. So those are my 2 semicircles. So then what this was based off of is the idea that each semicircle has an area that we know is 1/2 pi r squared. They're not just an area though. My red pen, those semicircles would have some sort of a width. So that's why we then jump from an area to a volume as we gave it a 3rd dimension. We would jam as many semicircles as we possibly could in there, and then we want to add them. So that's what the integral then does for us. So that was the setup for these. So for this particular problem, we have constants of 1/2 and pi out in front. Our limits would not have changed. We're still going to go 0 to 2. It's the same setup from number 1. But we can see I've drawn in 2 different semicircles in there. The radius is going to be different for each of them. So we're going to have to define that using a variable, since it's a variable radius. Our width, since these are drawn in vertically, is still measured as the change along the x-axis. So the semicircle that you have drawn in, draw in your radius. I'll draw it into my 2. And then we have always talked, it's always somehow going to be a top minus bottom or right minus left. So the radius that I have for these are vertical. Therefore, the only way to define that is going to be a top minus a bottom. So if I now try to define that radius, I pretty clearly have something on top. The line 4 is on top. So I'm going to do 4 minus. But the bottom of my radius, both of these here, and any that you're looking at on your paper, is just sort of out there in space. There's nothing bordering it on the bottom. So that's not uncommon. What we talked about then is let's extend it until we actually get something on the bottom, which is now, what was that, x squared. But then we would have to understand we're no longer talking about a radius if we do that, that we've just defined our diameter. And since I want the radius, then what I would do is take that diameter expression and know that that would then have to get cut in half. Without a calculator, evaluating this by hand is pretty messy. So when they give you a messier one, they'll just ask you to set it up, and then they'll say, do not evaluate it. So you can just leave that just like this. That's our cross section. So we did semicircles, circles, squares, and then equilateral triangles. The other thing they will do, just in case, is give you the graph, and then there's no excuse that we don't know what the graph looks like, right? And that's what number 3 is. This one I want you to see if you can set this up. So let's read it and see if you remember what method we would use. So find the volume of the solid created when the region shown below is revolved around the x-axis. So remember how we can now, this was the 3rd thing we did. This is when we started rotating it around the x-axis. Looks like this. And then now, without me telling you specifically what method to use, you had to identify, do I use a disc, a washer, or a cylinder? So this I want you to take a minute and see if we know which one this would be. So the way we talked about then deciding which is best, just like number 1, we can only deal when we did areas, either with vertical rectangles in here or a horizontal rectangle in here. That was it. There are only two options. So when we come down here, that's what you have to decide. The way this is written in terms of x, so it's kind of normal, it looks normal, we could graph that normally on our calculator. That implies we would want to do this with a vertical rectangle in here. So whatever happens when I rotate that vertical rectangle around, whatever figure you get, that's your best bet. So as I rotate this around, hopefully we would see that this forms a disk. So the disk is our best bet. All a disk is a circle. So that's why the disk method is pi r squared, and then they obviously have a width to them. Since it's vertical, is going to be our change in x. Since our limits, since we're in terms of x, our limits are really easy. Just look where we start out in terms of x and where we end in terms of x, so 0 to 4. If I now draw on the radius to my circle, draw on the radius to your circle, now we do have a clear top curve, and we do have a clear bottom curve, so there's no need to do a diameter and cut that in half. The top of every radius would be root x, the bottom of every radius would be 0. The thing I would harp on, if we were able to give a non-calculator test, which again, we really can't because I just don't know if you're using a calculator or not, is I would write this out. The setup is easy, that we should be good at. We've quizzed on it, we spent a week on these types of problems. The big thing is number 2, and that is you always want to make sure that you completely simplify the integral and make sure that gets done before you do step 3, which is your antiderivative. Because some people tend to skip that second step and then make up antiderivatives that don't really exist. Sorry, that got a little messy there. In regards to this question, what that means is I'm going to still have pi 0 to 4, but don't we really just have root x squared, which just gives us a simple little integral of x dx. That's that integral simplified. Now we can go through with the antiderivative like we did in number 1. Upper limit goes in first. Throw in a lower limit, and then that ends up being our answer, just 8 pi. All right. All right, real quick, we'll try to get 4 done, and then 5 I definitely want you to see, because 5 is probably the hardest one on here. So number 4, although 4 is also along those lines. Number 4, same exact area. So they would tell you to use this same region that we had up above. This time you're going to do cross sections. So we're going to take this space. We're going to be putting, in this case, squares on top. But this now says perpendicular to your y-axis. I did not do this to you on your quiz. Decent chance, and you're going to see this on the test because this is a little bit now harder. So you're going to take your squares, and we're going to put the squares horizontally in. Perpendicular to the y-axis means we're horizontal. So take your square, put it in horizontally here. And I'm sorry I can't draw this very well. Think of a piece of paper now sticking up. It won't look like this very well, but think of it kind of like this. Move this over for people in the building. There you go. Because that is now horizontal, when we go to set up our integral, it's a square. So all we were really doing is adding up a bunch of side squareds. But the width of all of those now horizontally would get measured as the change that they would take up along the y-axis. Because of that, everything has to be defined in terms of y. When we go to define our side, the side that lies on here is now a horizontal side. So I've got to do a right minus a left. So the right-hand side is obviously the 4 that's given to us. The left-hand side is our curve. Remember what the curve was above. It's y equals x squared. But what we can't do is say 4 minus x squared, because then we have x's and y's together. So this is one where we need to real quick solve this equation and say that x is equal to root y. That's how we're going to enter that into our integral. right, less than a minute. Let me hustle through here. Make sure your limits are y's. The lower y value down here is definitely a 0. And then our upper limit would be the y coordinate where those two guys would have intersected. That is the intersection of root y and 4. So our upper limit should end up being 16.
X squared, 4 minus X squared, but what's the X squared equals Y? I never got that. Why would you just put a Y instead of root?
Okay, we'll see you guys. Ethan has a question, but we're good. All right, we'll pick up with number 5 tomorrow. Okay, say that again now.
So if you said 4 minus X squared, but X squared equals Y, why not 4 minus Y instead of 4 minus root? Like, I get it. Which